Hello everyone and a very good evening to another session. Apologies for the delay. This was supposed to be out by 9 p.m. but I guess you'll see this a little bit later. We got a little bit delayed, so do bear with us. For those of you who don't know what's going on, first things first is to subscribe to this channel. We are doing some amazing product based questions, that is product companies based questions. Today's question has come from this company called, a very famous company, which is called Google. So it's a Google question. It's called router hacking, and this is actually very similar. I think it's 90% similar to the question that was asked by Google. This is day number 5 in our daily challenges for September 2020. And if you don't know about this, I'll just tell you a little bit in our rules section. So these are the rules. We started it right at 24th September. There have been 5 days now. So this is day number 5. Tomorrow we'll have day number 6 and then day number 7. So only 2 more days left. You can still go and attempt some of these questions, and if you attempt all of them before day 7, you can still have a chance of actually being on top of the leaderboard. So click on this link above. I'll also click it and show you how to get there. But you click on this link. Every day 6 o'clock a challenge will open. Every day, ideally 9 p.m. the solution is released, although today we are a little bit delayed. First to crack the challenge is on top of the leaderboard, and we've made this especially for all of the students to understand what their level is when it comes to product-based companies. If you are not at that correct level, then take your time and actually prepare. If you're there, then this is just another practice for you. So today's question, and I'll open it up on the Edyst platform. Today's question is challenge number 5. It's called router hacking. Let me just open it up. Yeah. So this is the question called router hacking over here, right? And let's click this question. So the question is like this: you have a system of n routers which are interconnected and can be represented as a tree where there is only one main router, which is the root of the tree, and ID is 1. Leaf routers are those which is not the main router and have exactly one router connected to them. So it's a typical tree. Like there's actually given a diagram also over here that this is the root. Let's say this 1 is the root, right? And 5, 6 are the leaves, right? And 3, 4 are also the leaves, because they are only connected to one other element and they don't have children of their own. So if they had children, then they would have there would be 2 elements, right? They would be connected to 2 elements, and therefore they wouldn't be leaves. So we have it like this. And so now the issue is, what you have is the information flow starts from the main router, and information is passed from one router to another, which are directly connected to that router, excluding the router from where the information came from. Something very simple, that the router's information starts at 1, and if you want to pass it on to 6, it will go 1, 2 and 6. It will never go 1, 2, 1, 2, 6, right? So it won't go back and forth. Once it's gone to 2, it's not going to come back to 1 again, right? So there is this over there. So that's what this means. Now there are 2 types of hackers. So basically I'll just cut the story short. What's going to happen is, we want to break certain routers and we want to repair certain routers, right? So routers or routers or whatever you want to call it, you want to break certain ones and you want to repair certain ones. Now the rule to break a router is that the path from the main router to that target router is clear. So let's say if I want to break router number, which one is that? Yeah, so let me say I want to break router number 2. So the path from 1 to 2 should be clear, and from 2 till all its subtrees should also be clear. That's what we are saying, right? So yeah, so we have path from 1 to 2 is clear, and the path from 2 to all of his subtrees should also be clear. So the path from main router to the target router is clear. The path from target router to all leaf routers who get the information directly or indirectly from the target router is also clear, right? So assuming, let's say you broke, so if you broke number 5, let's say first, okay, 5 is easy to break because it has no children below it, and it's the first to be broken. So the first to be broken will always be broken. So I broke 5. Then if I go to break 2, I can't really break 2, because even though 2's parents are not broken, 2's children, one of the children is broken, right? So 2's 5 is broken. So 2 has a subtree with a broken node, right? So that's what this thing is. So you can only break there. Repairing you can do anytime. So the only caveat in repairing, the only condition in repairing is that the node should be broken in the first place. That's it. So let's say I say that go and repair 3. Well, if 3 is not broken, then you can't really repair it. So as I say, if it ain't broke, don't fix it. It's kind of like that. All right. So the question becomes, basically it transposes itself very well into a trees question basically, where what you're supposed to do is the input format is like this, right? Where you're given the number of nodes, you're also given how each like the adjacency for each node, and what you're told is 1 will always be the main node, right? So the main router is going to be 1, all of the others. So if 1 is connected to 2, it means that 2 is a child of 1, 3 is a child of 1, 4 is a child of 1. We could have written this 2 1 also, and that wouldn't be a problem because we know that 1 is the main router. Everything else connected to 1 is a child. Anything else connected to that is also the child of that. So it keeps going like that. It becomes a tree basically, right? Now then these are three commands: info, black, and white. These are the 3 commands. Info will mean what is just the information? Is this node working? Is it not working? Or is this router working or not working? Black means that destroy this router. White means that repair this router, right? So that's what we have to do. For each of them we have to give an output. So for info we have to give either working or broken. For black we have to return 1 or 0. 1 would mean that we just broke it. 0 would mean that it's not possible to break. When is it not possible to break? As we just discussed, if either the parent is if one of the parents are broken or one of the subtrees has a broken node, then also it's not possible to break. Or if it's already broken, then I can't break it again, right? Similarly with repairing, I can repair if it's broken, otherwise I can't really repair it, right? So that's what this question comes down to. So let's look at the approach in the slides. So if you still didn't understand the question, by the way, I will urge you to just pause your video right now, go to the question, check out the question properly, because trees and graph sorts of questions you really need to understand fully, and then only you can go forward. So I've given you a gist, but if you want to take some time, take out some time and actually read the question first, and then you can go ahead. The link I already mentioned in the slides earlier, and you could also check it out in the description below. So in the description below also you have the link, right? So just going to the slides, right? 1 second. Yeah, so we have this. So what we're saying is one of the approaches we can do in a brute force way, right? And this is the simple way you can do it, is that in each query traverse to the given node. So if you have to break, I'm covering break right now, but repair is super easy, so we'll come to repair in a bit. But if you want to break a node, what you do is you traverse to that given node. If you encounter any broken router, then it's not possible. So on the way to that target, if you encountered any broken router, then it's not possible. If we encounter any broken router in the subtree of the node, so for each subtree you will further go into that from the target to each of its sub nodes, you will go and try to get to check if it's broken or not, right? If any subtree has a broken node, then it's also not possible. Otherwise it's possible, right? The other case also is if the router is already broken. Not possible. Sorry, 1 second. Not possible, right? So then also it's not possible. So what we're going to do and how do we traverse to that? So there is this concept in trees called depth first search. You can just use depth first search to get to your target. I'll explain all of that in just a bit, but you'll actually just use the depth first search, that is go to your target. If while going to the target you found any broken nodes, then this entire node is not possible. That is, it's not possible to break this. If from that target node till the end or through all its subtrees, if you found any broken node, then also it's not possible, because that's the condition given. So depth first search in the worst case scenario can be order n, and since you're going to do this for every query, it can be order qn. Because for repair it's roughly similar. Repair also has a similar order. I'll just come to repair in a bit, but repair also is just about the similar order, so it'd be order q into n. Now, while I think it was working today, generally speaking, we allowed brute force to work out, even though the constraints didn't really allow it, but we did allow brute force to work out. So I'll just share the constraints as well. The number of queries we have can go up to 1 second. Where is that? Yeah. So the number of queries we have can go up to 1000, and n itself can go up to 1000. So 1000 into 1000, 10 raised to 6, as I mentioned earlier. That's really not going to work out, but we allowed it today. We did certain things so that you could also do a brute force and get away with it. Having said that, the optimal approach, let's come to the optimal approach, and this is a fairly standard approach in most trees questions. So even though Google asked this, it's not a super difficult approach, because most trees question rely on this approach, and I'll tell you what that approach is, right? So number one, beforehand keep the parents of each node stored, and this is one of the most standard things you will do in trees. If you don't learn anything from this, if you probably don't even go and apply the solution, the least I can say is learn that one of the tactics you can use in a trees question is to store what the parent is, because oftentimes you will need to know what the parent is, right? So here what we are saying is, let's say we store the node of the parent of each node, right? So now if I want to check if I can break this node or not, I have to check two parts, right? I have to check the parents and I have to check the subtree itself, right? So all I can do is I can keep going through the parents. So for example, if I want to break 3 in the given question, so one second, if I wanted to break over here, for example, if I want to break 5, right? What I can do is I can, and let's say there is subtree below 5 also. What I can do is I can go and check the parents first. Is 2 there? Is 1 there? Right? That's one thing I can do. That is 2 a what I could say, is 2 broken? No. Is 1 broken? No. Great. That means that at least on the parent side we don't have any issue. So for 5 store that the parent is 2, for 2 store that the parent is 1. So that from 5 to going to 2, 2 to go to 1, it's very simple to figure out what it is. If we had done the earlier way of brute force, right, what would be our problem? Our problem would be, first, we don't even know where 5 is. So from 1, we would have to do a depth first search to figure out where 5 is. And while we are going to 5, we have to keep storing whether we encountered any broken things on the way to 5 or not, right? But this optimal approach, what we are saying is, for 5 store the parent, for 2 also store the parent, so that I can very easily get all the way to the main node. On the way to the main node, if I found any broken nodes, if I find any broken nodes, then I know that it is not possible, right? So that's one. So if any parent is broken, then it's impossible. If any subtree has broken nodes, then it's also impossible. Now, how do we figure out whether a subtree has broken nodes or not? So what we're going to do here is, whenever a node breaks, right, increments parents counts of broken nodes, right? Now I'll just explain what's happening here. Basically, let's say I break the first node. In the first node, I can always break. There is not going to be any issues. When I break the first node, I say, okay, this node is broken. So if I go back here, let's say I say, okay, let me break 5 at first. Yeah, 5 is easy to break. It's the first one. I break 5. Now also what you should do is, remember that 2 has 1 broken node in its subtree. Remember that 1 has 1 broken node in its subtree. So basically keep going to its parents, right? And also add that its subtree has 1 broken node, right? So while we are checking the parents, if there are any broken, if there are none broken, right? What you should check for then is, the current subtree that I'm on, does it have any broken nodes as its children, right? So in the first one, what will I do? I'll go to 5 and I'll say, okay, it's the first one. I can just break it. There's no problem. So I'll break that 2 is, 5 is broken and 2 has 1 broken subtree or 1 broken node in its subtree, and 1 also has 1 broken node in its subtree. Great. Next time when I go to break, let's say 1, I can't really break 1. Because 1 I already know has 1 broken node in its subtree. How did I know that? In the previous, when I broke 5, I stored it, right? So I stored it over here. So what I'll do is, I'll store, whenever a node breaks, I will increment the parents count of broken nodes, right? Broken nodes in its subtrees. So I'll say broken nodes in subtree, right? I'm going to do this. Now, if the subtree has any broken nodes, so whenever I go to break, I'll start from here. If any parent is broken, impossible. Not possible. So if subtree has any broken nodes, impossible. If node is already broken, then also it's impossible. Else, right, what we're going to do is this. So I'll just actually bring this down here to remove the confusion. Else what I'll do is, first mark node as broken, right? So first I'm going to mark that the node is broken over here, right? Yeah, so first I'm going to mark that the node is broken, right? And increment parents count of broken nodes in subtree. That is basically, for each parent, say that, you know what, there is 1 more broken node in this subtree, right? So that way, all I can do is, I will just have to traverse the parents every time, right? So the order goes from order n to order h, where h is the height of the tree, because which in the worst case can go to order n, because, you know, if you have a linked list as a given tree, that's the edge case, which I'll come to later. That is possible. So that's order n in the worst case. But order h is the height of the tree, because you are not going through all branches, you're only going through the concerned branch, right? So that's the optimal version. Now, how do we do the repair? If we do this way, how do we do the repair? Well, there are 2 things we need to do. So let me just quickly write down here. To repair, the same thing we can do, and I'll just come to this first part also here. Beforehand keeps the parent of each node stored. Yeah, we can do this, right? How do we do that? I think some of you noticed I put a how over there. I'll come to that at the end, right? So how do we do that? Let's say we have the parents. Let's not go into how we can get the parents right now. To repair, what we're going to do is, if simply put, what we'll say is, if working, then impossible to repair because it's already working, right? If it's broken, then what you'll do is, if broken, then what you'll do is mark, sorry for that, yeah, okay, mark as working, right? So if it's already broken, then I'll mark it as working, and after I marked it as working, what should I do? Yeah, decrement broken nodes of parents, right? So for example, I first marked 5 as not working. I broke 5, so that means that excuse me. So once I did that 5 is not working, then I marked that 2 and 1 each have one broken node in its subtree. The moment I repair 5 again, I have to go to 2 and 1 and increments and decrement, saying that, oh, now there are 0 and 0 nodes that are not working, right? That means number of broken nodes are 0. So I have to undo what I used to do for the breakage, right? That's what I'm doing. Decrement broken nodes of parents. That's as simple as that. So this is the repair part. Now the question arises, in the given question, we are not given a parent-child relationship. That is, we are just told that these are connected to each other, and you know, the information flow thing is given to us. So how can we know that which one is the parent of each node, right? For each node, how do we know who is the parent? The simple answer to that is, we know that 1 is the main router. So 1 will be the parent of all its adjacent elements. That we know for sure. So even in the given question, if I go back to the question over here, second. Yeah. So if I go back to the question over here, what I'll get is, even in this question, we are given that 1 is adjacent to 2, 1 is adjacent to 3, and 1 is adjacent to 4. Since we know that 1 will be the main router, we know that 2, 3, and 4 are its direct children. Then what we should do is take 2 as a parent and see all of its adjacent elements. So what we got is 5, 2, and 6, 2. This means that 2 will be the parent of 5 and 6, right? Because 2 was connected to 1, right? So after 1 came 2, and after 2 has to come 5 and 6, right? Below 2 has to come 5 and 6. That's how we know this is the case over here. Below 2, 5 and 6 have to come, and 3 and 4 were adjacent to 1. Therefore, they are children of 1. But how do we do this? The simple answer is, start with 1 and start doing a depth first search, right? When you do a depth first search, you have to do this once. In the brute force, you have to do this again and again. What we are saying is, do it once and establish who is the parent of which node, right? For each node, establish the parents. Once you've established the parents, then all of these queries become easy. They can happen in order h time. So this order n of depth first search is amortized over all of these queries. Now, if all of these new terms, order n, order h, order q being amortized, is new to you, then you really need to start preparing for algorithms data structures, and do sign up for an upcoming course that we're going to have. If you're interested in that, let us know in the comments below. But yeah, these are all very standard terms of algorithms, data structures, amortizing, and all when it comes to optimizing things, right? So that's there. Now for this one, I'm not going to code it live in front of you. I'll actually open up the code and show you what are the different things that are going to happen. I will lose 50 points, but hey, that's fine for me. If you guys want the exact code, then you will also have to lose 50 points to get it. So since many of you are asking C++, we have a C++ solution, although I can also show it in Python. Both of them are there. But yeah, we have both sorts of solutions over here with extensive comments over there. Let me just pick it up in Python and show you what's happening. And you can read the C++ solution as well over there, right? Okay, so I'll just put it up in Python over here. Yeah, here we go. All right. So let's start. These are some of the methods, and I'll just come to that. And you will see that there will be a lot of recursion because any trees question requires recursion. Okay. So n is int input. We have a dictionary of parents. This is basically what I'm going to store is for each node who is the parent is what I'm going to store here. Broken is a set. We want to store which all nodes are broken. This is the set. Broken subtree is for each node, how many nodes are there in the subtree which are broken. So that's what broken subtree is. Adjacent is nothing but the adjacency matrix or the adjacency lists. For each node, we will store what are all of the adjacent elements to that node. Okay. So that's what we're doing here. What we say is that the broken subtree of n, we know that there are about n edges, there are n vertices that's given to us. So what we're saying is that, and it starts from 1, goes all the way to n. So what we're saying is that basically here we're just marking that the broken for n is 0, just like that, because we have only n minus 1 edges, and so after n input we are given n minus 1 edges. So this is the loop for that. In each loop, whenever an edge has to be created, we first get which 2 vertices the edge has to be created in, and we add this to that, right? So we append, if it already exists, then we append it, otherwise we create a new edge, right? And this is fairly standard for it, so I'm just going to skip through this part, but it's fairly standard on how you can create an adjacency matrix or adjacency list. Just have a look at it. You can pause the video and check out, but it's a fairly standard way of making an adjacency list. What we are also doing is that for each node, we are saying that the number of broken nodes in its subtree is 0. Initially, because we have not even broken anything, we can say this, so it's fine. And what we'll also do is that if if there are any nodes, or rather if one has any neighbors, because one has to have certain neighbors. So if one has any neighbors, then what we'll do is we'll mark that 1 is the parent of all of its adjacent elements, and this set parents is a recursive function. So if I go to the set parents function, what you will see is what I'm doing is for each node I am marking something as a parent node, right? And storing it in the parent dictionary. So what I'm saying here is basically there is a current. What I'll say is that for this node, mark the parent node as its parent node in the parent dictionary, right? And for each adjacent node, what you have to do is mark that also as a child node of this particular node, except for the node that we came from, right? So if I not equal to parent node, that means it's adjacent, which means that my current node is the parent of all of my adjacent elements. Just like for 1, we have all of its adjacent elements as its children, right? So that's what the set parents is doing, and through a depth first search we are actually getting to that. But however, if 1 doesn't have any adjacent elements, it means that where is that? Yeah, if 1 doesn't have any adjacent elements, sorry, one second, this was here. Yeah, if 1 doesn't have any adjacent elements, it means that there is only one node, because if there is more than one node, then one has to have adjacent elements. But if 1 does not have any adjacent element, means only one node, which means that you don't even have to do anything. All the answers will just be like based on 1. Okay. Now what we have here is q is equal to int input, which is nothing but the queries. So we're getting all the queries over here. You can just write it as queries also. That's also fine. Okay, it's not taking it. Okay, anyways. So q is equal to int input. We get the command and the node. If the command is black, that means you have to break the node. If command is white, you have to repair the node. If the command is info, then we just have to mention if it's broken or if it's working, right? Now let's have a look at both the broken and the repair node function. So we have the broken node function over here. Sorry, break node function over here. What you say is if it's already broken, return 0. Great. Or if any of its parents are broken, so this is us traversing the parents. We take a temp node and we keep going into the parent of it, return 0. So as long as if there is a parent, we'll keep going further and further and further. If we find anyone that's broken, we return 0. Otherwise, we break out of this array, break out of this loop, and we say if any subtree is greater than 0, that is if there are any broken nodes in the subtree, then also mark it as return 0. Otherwise, what you do is all of these conditions passed and it was not at all broken. Then what you do is add this node to the broken set, saying that okay, now we can break this. And what you should do is for each of its parents, mark that there is one extra node, one additional node that has been broken in its subtree. So that's what we're doing over here. And then we return 1 saying that it's broken. For the repairing node part, it's just that only. If the node is not broken, then you return 0. Otherwise, remove it from broken. And for each of its parent, mark it as that there is one less broken subtree, right? One less broken element in its subtree. So that's what you should mark it as over there and return 1. So yeah, I'll just run it and show you also that it does work. Yeah, so it does work and it's the optimal solution. And really, it's a trees question. I know a lot of you are generally not that well versed with trees, and you're not sure about how to handle trees questions. So I hope I've showed you. It's a very common tactic in trees question to save the parent of the particular node. In fact, what you can also expect is in interviews, once let's say you've adopted this approach, the interviewer can actually ask you, let's say you're not allowed to save the parent, then what do you do? So that's also in many questions this also happens. So this was the brute force which we optimized by actually saving all the parents. And how did we save the parents? By getting DFS done once, as opposed to in brute force we were doing it every time. Here we did DFS once, got all the parents, and that's how we got the solution for this question. So that's it for today. I hope you understood it. If you didn't, the solutions are available in exchange for points, so you lose some points, but hey, the solution is there. Go through the solution. Tomorrow is going to be an interesting question. Tomorrow is a Facebook based question. I think the next 2 days are Facebook based question, and they're really, really good and interesting. So do stay tuned for tomorrow. Once again, if you like what we're doing, subscribe to this channel, like this video so that more people come to know about it. And if you are interested in upping your algorithms, game that is getting more into algorithms, data structures, learning from me directly, and learning from the entire Edyst team, one-on-one mentorship, and so on, do let us know in the comments below whether you'd be interested in a course like this. From tomorrow onwards, we'll start making announcements, and the first few students will get something special as well. So thanks everybody for joining in today. I'll see you all tomorrow for another session. Today was router hacking, formerly asked Google question. Let's wait for tomorrow for another great question. Thanks everybody for joining, and I'll see you all tomorrow. Thank you.